Welcome back to QHSE Talks. So imagine for a second that you are standing outside a massive chemical storage tank.
Okay, a pretty common scenario for a safety pro.
Right. And you are looking through the hatch and you suddenly see a worker inside they just collapse to the floor.
Yeah.
Your human instinct, your absolute deepest biological, psychological drive is to rush in and save them.
Of course it is. It's empathy.
You just want to, hold your breath, scramble through that narrow hatch, grab them by the shoulders, and drag them out to fresh air.
Yeah, you don't even think about it.
But historically, in the world of industrial safety, obeying that perfectly natural instinct is exactly how more than 50% of people die in these environments.
It is, it's honestly the most tragic statistic we deal with. We actually call it the heroic fatality.
The heroic fatality, wow.
Yeah, because the original victim collapses because the air is lethal, right?
Yeah.
And then the untrained rescuer...
Who is just driven by pure adrenaline at this point.
Exactly. Driven by pure adrenaline and just wanting to help their friend. They rush into that exact same lethal environment and instantly they double the body count.
Which is just a grim, grim reality.
Yeah.
And that is exactly why we're here today. Today, our mission on QHSE Talks is exploring the essential safety fundamentals of confined spaces.
It's a massive, massive topic.
It really is. And for those of you listening who are, studying for the ASP, the Associate Safety Professional exam, this is an absolutely essential skill to pass that exam.
Yeah. Domain 2, topic 8. It's heavily tested.
Right. But taking a step back from the exam room, understanding this topic in detail is really the difference between a routine maintenance shutdown and, a catastrophic multi-fatality incident happening on your watch.
It's the ultimate proving ground for your mindset as a safety professional.
Yeah.
I really want to frame this right out of the gate with a core philosophy from the AST prep materials.
Okay, let's hear it.
A true safety professional does not just calculate air volumes or check boxes on a permit clipboard.
Right, it's not just a paperwork exercise.
Exactly. If you want to actually protect workers, you have to be able to interpret those results, apply massive safety margins, and, fully understand the physical and physiological consequences of that environment.
Yeah, you have to see the big picture.
Right. The guidelines for risk-based process safety put it perfectly, actually. Standing still. Just congratulating ourselves on the accidents that didn't happen yesterday.
That's not going to prevent the disaster brewing today.
Spot on. We had to actively make risk-informed decisions to move forward safely.
Right, because we aren't just safety historians, analyzing past disasters.
Yeah.
We are actively engineering the work environment to prevent the next one.
We are engineers of safe work, yes.
So whether you are reviewing your notes for the exam or lacing up your boots for a site inspection later today, this QHSE Talks is going to give you the analytical framework to spot those invisible, counterintuitive hazards.
The ones that everyone else on the job site is just going to walk right past.
Exactly. So let's get right into it. Let's start with the geometry of danger. Because, before we can protect a worker from a hazard, we have to actually recognize that the hazard exists.
Which sounds basic, but it's where everything falls apart.
Right. Historically, the initial failure in the whole disaster chain is just failing to recognize an area as a confined space in the first place.
It happens all the time. People hear the phrase confined space, and they immediately picture this cartoonish scenario.
Like a tiny, dark, incredibly claustrophobic metal box.
Yeah, exactly. But the regulatory and technical definition has absolutely nothing to do with feeling claustrophobic. It is highly specific.
So what are we actually looking for?
Well, for a space to meet the basic definition, it has to meet 3 strict criteria simultaneously. First off, it must be large enough and so configured that an employee can bodily enter and perform assigned work.
Okay, bodily enter. So if I'm just reaching my arm into a pipe to clear a jam,
That is not a confined space. If only your arm fits, it doesn't meet the criteria.
Got it. What's the second one?
Second, it must have restricted or limited means of entry or exit.
So we're talking about having to climb down a 20-foot ladder or crawl through a narrow pipe or squeeze through a 20-inch access hatch.
Right. You can't just walk out a normal doorway if things go wrong. And there's the third criterion, which honestly feels like the absolute linchpin of the whole concept.
Which is what?
It is not designed for continuous human occupancy.
Oh, man. Let's really pull that apart. Because when you look at an environment designed for humans, like an office or a control room or even a normal factory floor, the architecture is inherently forgiving.
Highly forgiving, yeah.
It has HVAC systems constantly turning over fresh air. It has ambient lighting.
Multiple clearly marked doors.
Yeah. Ground level doors with push bars so you can just bolt out of there in an emergency.
Exactly. Human-centric architecture supports biological life. But the spaces we are talking about today, the storage tanks, the grain silos, municipal sewers, chemical reactors,
they are completely hostile to biology.
hostile is the perfect word. The space was engineered for a process, not a person. It was built to hold 50,000 gallons of crude oil or to ferment yeast.
It was never built with our respiratory systems or our physical mobility in mind.
Not even a little bit. And because these spaces lack normal ventilation, any hazard that gets introduced into them or naturally off gases inside them, it's trapped.
It accumulates.
Right, it accumulates. The margin for error that you have in an open room drops to absolute zero.
It's basically like stepping into a mechanical trap. I mean, it might look perfectly clean and completely dormant when it's totally empty, but the architecture itself is just waiting to amplify whatever hazard you introduce.
That's a great analogy.
But let me clarify something that often trips people up when they first study this for the ASP.
Sure, lay it on me.
Let's imagine a brand new, massive, underground concrete pit. It is 30 feet deep. It's totally empty. The air is perfectly clean. There's nothing down there but some dust.
Okay, a clean pit.
Right. But it's really hard to get out of because you need an extension ladder. So does that empty, perfectly clean pit still get classified as a confined space?
Yes.
Even though there's no toxic gas or anything?
Even then, it fits the baseline definition perfectly. You can bodily enter it, it is restricted for entry and exit, and you aren't meant to live down there.
Okay, so it gets the label.
But, and this is huge, but that baseline label is just step one. What the ASP framework and real-world safety professionals really focus on is what elevates that basic space into a permit-required confined space.
Which you'll constantly see abbreviated as PRCS.
Right, PRCS. To cross that critical threshold from a basic space to a permit-required space, the environment must exhibit at least one additional serious hazard.
Okay, so a basic confined space is a potential trap, but the permit-required label means the trap is actively armed.
I love that. Yes, the trap is armed.
So what exactly arms it? What are the 4 PRCS characteristics?
Well, it only takes one of these 4 to trigger the permit requirement. Number 1, it contains or has the potential to contain a hazardous atmosphere.
That's the big one.
Huge. Number 2, it contains a material that has the potential for engulfing an entrant.
Like grain or sand, got it.
Number 3, it has an internal configuration such that an entrant could be trapped or asphyxiated by inwardly converging walls or by a floor which slopes downward and tapers.
Like a funnel.
Exactly. And number 4 is this broad critical catch-all. It contains any other recognized serious safety or health hazard.
So going back to that empty, clean, concrete pit, it's just a basic confined space.
Right.
But the very moment a contractor lowers a gas-powered water pump into the bottom to, clear out some rainwater, they are introducing carbon monoxide exhaust.
Instantly.
Or say an electrician discovers exposed live 480-volt wires down there instantly, the classification upgrades, right?
Yes. It is now a permit-required confined space. The introduction of the hazard completely transforms the regulatory, operational, and legal reality of that space.
And because that architecture is so unforgiving, like we said, we have to look really closely at the most immediate threats. And by far, the most insidious, pervasive threat in these environments is the air itself.
The invisible killers.
Yeah, the invisible killers. And this is where the exam and the job itself demands absolute precision from you. We aren't just using subjective terms like stuffy or foul air.
No, we are dealing with rigid, scientifically calculated thresholds.
Right. Let's start with oxygen, because we all need it. What exactly constitutes a hazardous oxygen level?
Well, normal ambient atmospheric air is roughly 20.9% oxygen.
20.9, okay.
A hazardous atmosphere is legally defined as an oxygen deficiency, which is any concentration below 19.5%, or, on the flip side, an oxygen enrichment, which is any concentration above 23.5%.
I really want to stop on that 19.5% number for a second, because understanding the why behind that specific number is absolutely crucial.
It is. It's a key concept.
At normal sea level, we are breathing 20.9%. If it drops to 19.5, that is only a 1.4% drop.
Right.
Why is the alarm ringing so early? I feel like a lot of workers might look at their monitor and think, hey, there's still plenty of oxygen. It's basically 20%. What's the big deal?
That is a brilliant point, and it perfectly highlights the difference between just reading a textbook to pass a test and actually understanding human physiology.
Right.
You have to ask yourself why the oxygen level dropped by 1.4%. In a confined space, oxygen doesn't just mysteriously vanish into thin air.
It has to go somewhere.
It is being actively consumed or displaced. If it dropped to 19.5, something is actively happening in that room.
Like what? What consumes oxygen in an empty tank?
Rust. Simply rusting. Maybe rust is forming on the bare steel walls of the tank, which literally consumes oxygen from the air in an oxidation reaction.
Wow, just the walls resting can drop the oxygen that much.
Yes. Over time, in a sealed space, absolutely. Or maybe another gas, like argon or nitrogen, is leaking into the space from a pipe and physically pushing the oxygen out.
So that 1.4% drop isn't just about the oxygen itself.
No, it's your early warning indicator. It tells you that a chemical or physical process is actively degrading the environment right now.
That is terrifying.
And furthermore, when oxygen drops down into the 16% range, human physiology starts failing rapidly.
What happens at 16%?
Your judgment becomes severely impaired, your motor coordination drops, and this is the scary part. You might actually feel a false sense of euphoria right before you pass out.
You feel happy.
You feel fine. You don't realize you're suffocating. So that 19.5% threshold gives you the necessary buffer to realize the environment is changing and evacuate before cognitive impairment physically prevents you from climbing the ladder.
That makes total sense. It's not that 19.5 will kill you, it's that the trend line is pointing straight toward a lethal atmosphere, and you need your wits about you to escape before it hits 16.
Exactly.
Okay, so that's oxygen. Now, what about flammability? What are the exact thresholds we need to look out for there?
We have a hazardous atmosphere if flammable gas, vapor, or mist is present at more than 10% of its lower flammable limit, or LFL.
And LFL is often used interchangeably with LEL, right? Lower explosive limit.
Yeah, functionally in the field, LFL and LEL are treated as the same concept. Additionally, if there is airborne combustible dust at a concentration that meets or exceeds its LFL, that's a serious hazard.
Dust explosions are massive.
They level entire factories.
Yeah.
And finally, any condition that is immediately dangerous to life or health, what we call IDLH, constitutes a hazard.
Let's really explore that 10% LEL rule, because this is another massive safety margin. The lower explosive limit is the absolute minimum concentration of a gas in the air needed for it to ignite and explode, right?
Correct. If you are below the LEL, the air-fuel mixture is too lean to burn. There simply isn't enough fuel in the air to catch a spark.
So if the rule is to stop work and evacuate at 10% of the LEL, we're essentially stopping work when we only have 1/10 of the fuel required to cause an explosion.
That's right.
Why such a massive safety margin? I mean, why not wait until it hits 50% or even 75%?
Because of the complex physics of gas dispersion. If your calibrated monitor is reading 10% LEL right where you are standing, you are relying on a very dangerous assumption.
The assumption of perfect mixing.
Exactly. The assumption of perfect uniform mixing of the air inside that space. But unventilated spaces almost never have perfectly mixed air.
Right, it's not a sterile laboratory chamber.
No, there are dead zones. There are baffles. So while your monitor reads a safe 10% in the middle of the tank, a dark corner just 3 feet away might have a trapped pocket of vapor sitting at 80% LEL.
Just waiting for a spark.
Just waiting. Or consider this. The worker might be doing a task, say, shoveling sludge at the bottom of a petroleum tank.
Okay.
They break through a crust on that sludge, and suddenly a massive bubble of trapped hydrocarbon vapor is released directly into their workspace.
Oh, wow.
In a confined space, the atmosphere can jump from 10% LEL to 100% LEL in a matter of seconds.
Right. So again, at 10% LEL, you aren't waiting for the explosion to happen. You are buying yourself the operational runway to shut off your equipment, grab your tools, and evacuate the space before that localized pocket of gas expands and hits a spark.
It's all about buying time.
And beyond the flammability issues, we have the toxic hazards, things like carbon monoxide and hydrogen sulfide. The physiological mechanics of these gases are they're terrifying, honestly, because they rob you of your senses.
They absolutely do. Let's look at carbon monoxide first. It's a byproduct of incomplete combustion. So we're talking about gas-powered tools, welding operations, or even vehicle exhaust creeping in from outside the space.
And you can't see it or smell it.
It is completely colorless and completely odorless. And physiologically, it's an absolute nightmare.
How does it work in the body?
Well, carbon monoxide binds to the hemoglobin in your red blood cells roughly 200 to 250 times more aggressively than oxygen does.
250 times? That's insane.
It is. So even if the tank has perfectly normal oxygen levels sitting at 20.9%, the carbon monoxide essentially bullies the oxygen out of the way.
It just steals the seats on your red blood cells.
Exactly. It steals the seats. And so your brain suffocates while your lungs are pumping perfectly good air.
So you don't even feel like you are choking.
Not at all. You just feel a slight headache, maybe some profound fatigue, and then you lose consciousness.
And hydrogen sulfide, or H2S, that operates differently, right? But it's equally deceptive.
It is heavily present in sewers, paper mills, oil refineries, anywhere there's organic decay.
Yeah.
At low concentrations, it smells intensely like rotten eggs.
Everyone knows that smell.
Right. But here's the biological trap. At higher lethal concentrations, H2S rapidly paralyzes your olfactory nerves.
So your nose literally stops working.
Yes. You smell the rotten eggs, and then suddenly the smell goes away. And your brain tricks you into thinking, oh, the gas must have cleared out. I'm safe.
When in reality, the concentration just spiked to a lethal level, and you are literally seconds away from collapsing.
Exactly. Which is exactly why we cannot ever rely on our biological senses to evaluate a confined space.
We have to rely on technology.
Technology and rigid testing protocols. The standard mandates that technically competent personnel must evaluate the space using approved, calibrated direct reading instruments before any entry happens.
But having the right tool is only half the battle, right? I mean, the methodology of how you test the space is really where lives are saved or lost.
Yes. You have to account for a physical phenomenon known as stratification, or layering.
Right. I really want to paint a picture of this because it's a concept every safety professional needs to be able to visualize.
Go for it.
Think of the atmosphere inside a deep cylindrical manhole, less like a uniform room full of mixed air and more like a bottle of unmixed salad dressing.
Oh, that's a phenomenal mechanical analogy.
Right. The heavy ingredients sink to the bottom and the lighter oils float on top. Gases do the exact same thing based on their molecular weight relative to normal air.
They do. Normal air has a specific vapor density. Gases that are lighter than air, like methane, that's your lighter oil in the dressing, they will rise to the very top, sitting right under the manhole cover.
And gases that weigh roughly the same as air.
Gases like carbon monoxide will mix relatively evenly throughout the middle column of the space. And heavy gases, like hydrogen sulfide, will sink like a rock to the lowest, deepest points of the space.
So if you are the competent person doing the testing and you just crack open the manhole cover, stick your gas monitor probe in just like 6 inches below the rim, wait for a green light and say, okay, the air is clean.
You have only tested the methane layer.
Right. You have completely missed the lethal layer of hydrogen sulfide sitting 20 feet down at the bottom, which is exactly where the worker's head is going to be when they're standing down there working.
Exactly. You must drop the probe down and sample the atmosphere at the top, the middle, and the bottom.
Is there a rule of thumb for the distance?
A standard rule of thumb is testing every 4 feet of depth. And crucially, you have to pause long enough at each level for the sensors on the monitor to actually process the air.
Right, because the pump has to draw the air all the way up the tube.
Yes, which can take several seconds depending on the length of the sampling tube. If you just drop it down and pull it right back up, you're getting useless data.
But let me ask you this, because this is a point of real-world friction. Let's say I'm that competent tester. I diligently lower the probe. I test the top, the middle, the bottom. I wait the required time for the pump.
Okay.
Everything reads 0. Toxics are 0. LEL is 0. Oxygen is a beautiful 20.9%. I sign off on the permit. The tank is clean.
Sounds good so far.
Why can't we just clear that tank for the entire 8-hour maintenance shift? The hazard isn't there. We proved it scientifically. So why do we need to keep obsessing over the air?
Because that assumption is arguably the single most dangerous fallacy in industrial safety.
Really? The single most dangerous?
I believe so. The pre-entry test only tells you what the air is doing in that specific dormant millisecond. But a confined space is a dynamic, reactive environment.
What do you mean by reactive?
I mean, the very act of putting a human being inside it and having them perform work fundamentally alters the chemistry of the space.
How so? Give me a mechanical example of that.
Let's say the worker goes in to perform a welding repair on a stainless steel pipe. The pre-entry air was perfect, but the moment they strike the arc, the welding process is actively consuming oxygen from the air.
Oh, right.
Simultaneously, the shielding gas they are using, say, argon, is filling the space and displacing whatever oxygen is left.
And argon is heavier than air, right? So it's filling up from the bottom like water.
Exactly. And it gets worse. The extreme heat of the torch on the metal is generating toxic hexavalent chromium fumes, and it's generating carbon monoxide.
So they are literally creating a toxic soup.
Or consider a worker applying an epoxy coating to the inside of a water tank. The volatile organic compounds in that epoxy are rapidly evaporating into the confined air, dramatically spiking the LEL.
So the worker isn't just entering a hazardous environment, their work is actively manufacturing a hazardous environment.
Precisely. And that is why the ASP standard strictly requires continuous atmospheric monitoring.
Continuous, not just periodic.
Continuous. The gas monitor must be running, sniffing the air directly in the worker's breathing zone for the entire duration of the entry. If the work creates a toxic cloud, the monitor catches it before the worker's lungs do.
It's basically a continuous conversation with the environment.
That's a great way to put it.
Now, if the physical layout is that deceiving and the gases are actively trying to kill you, we really have to look the other ways these spaces operate like traps. And that brings us to the physical perils.
Yeah, it's not just what you breathe.
Right. Because it's not just the air. The very contents and geometry of the space can physically crush you. Let's talk about engulfment.
Engulfment is horrifying.
Yeah.
It is defined as the surrounding and effective capture of a person by a liquid or a finely divided solid substance.
When we say finely divided solids, we're talking about agricultural products, right? Like grain, corn, or soybeans in a silo.
Yes, or industrial materials like sand, gravel, coal dust, or dry fertilizer.
You know, grain bin entrapments are notoriously misunderstood by the general public. People tend to think of a silo full of corn like a swimming pool full of water.
They think they can just swim in it.
Exactly. They assume that if you fall in, you can just doggy paddle your way back to the surface. But grain doesn't act like a fluid. It acts like quicksand, and it exerts immense frictional force.
It does. Let's really break down the mechanics of compressive asphyxiation in a grain bin.
Okay, walk me through it.
If a worker is standing on what looks like a solid crust of grain, and a void opens up beneath them, usually because the grain is being drawn out from the bottom of the silo, they are pulled downward instantly.
Like someone pulled the rug out from under them.
Exactly. Once the grain reaches their chest, survival becomes incredibly difficult. Because every time the worker exhales, their chest cavity slightly contracts.
God.
And the loose grain instantly flows into that tiny millimeter of empty space, packing tightly against their ribs.
So it's essentially acting like a giant granular python. Every time you breathe out, it gets tighter.
Yes. When they try to inhale again, they literally cannot physically push the grain outward to expand their lungs. The human diaphragm simply does not have the muscular strength to move thousands of pounds of surrounding grain.
And you cannot just throw a rope down and pull the person out, right?
No. The sheer friction of the grain packing around the person's legs and torso is massive. If you put a harness on them and tried pulling on them with a winch, you could literally dislocate their spine before it pulls them free of the grain.
That is brutal. So how do you rescue them?
You have to build retaining walls around the victim, essentially creating a tube around them, and physically vacuum the grain away from them by hand. Is an absolute race against time.
Which really highlights why preventing the entry in the first place is so critical.
Exactly. And entrapment operates on a similar mechanical principle, but instead of the product doing the crushing, the architecture of the space does it.
Right. The definition specifically flags inwardly converging walls or floors that slope downward and taper.
Think of a cyclone dust collector or a large hopper. The walls slope down into a narrow funnel. If a worker slips, gravity wedges their body tighter and tighter into the narrow point of the V shape.
So the architecture physically acts like a vice.
Yes. Their own body weight becomes the force that compresses their chest cavity, leading to asphyxiation.
Man. So what other physical hazards are safety professionals evaluating before they sign off on a space? What else is on the checklist?
Well, you have to look at all potential energy sources. Is there high-pressure steam piped into this tank? A sudden release of steam in a confined area causes instantaneous, catastrophic thermal burns.
Because the steam has nowhere to vent.
Exactly. Are there high-pressure hydraulic lines? What about the electrical systems? You are often putting a worker inside a highly conductive, grounded steel vessel,
All right, they're basically standing inside a giant ground wire.
A simple fault in a power tool or an extension cord becomes a lethal electrocution hazard because the worker is quite literally standing inside the ground path.
You also have biological hazards, right? Like sewers, wastewater treatment plants, or even abandoned vaults that have accumulated animal waste.
Ooh, yeah. You were dealing with pathogens, bacteria, and viruses. And we cannot overlook the hazards created by the work activity itself.
Like what?
Take noise. If you take a grinder or pneumatic hammer and start working inside a steel tank, the acoustic energy has nowhere to go. It reverberates and amplifies off the curved steel walls, creating profound, immediate acoustic trauma.
You'll blow your eardrums out in seconds.
Easily. The same goes for temperature. A steel tank sitting in a rail yard in July is an oven. The steel absorbs solar radiation, the air inside doesn't move, and the worker inside wearing heavy protective clothing can succumb to extreme heat stroke in minutes.
It's an absolute gauntlet. But there is one specific scenario mentioned in the source literature that genuinely feels like the final boss of industrial safety.
I know exactly what you're going to say.
It's the concept of a confined space within a confined space. Let's break down the mechanics of why this is such a massive logistical nightmare.
It is a nightmare because it forces you to run multiple overlapping hazard assessments simultaneously.
Like nesting dolls of danger.
Yes. Imagine an industrial facility that has a massive, deep, open-topped concrete vault holding some pumps and piping. That vault is a confined space.
Okay, that's layer one.
Now, sitting inside that vault is a smaller, enclosed chemical storage tank. The tank needs internal maintenance. So the worker has to climb down into the vault, cross the floor, open the hatch of the tank, and climb inside the inner tank.
So if I'm the safety professional and I am hyper-focused on the toxic chemical vapors inside the inner tank, it is terrifyingly easy to suffer from tunnel vision and completely forget to analyze the hazards of the outer vault.
That is the cognitive trap. The outer vault might have an entirely different hazard profile.
What kind of hazards?
Well, it might be prone to rapid flooding from groundwater, creating an engulfment hazard. Or it might have heavier than air carbon dioxide pooling on the floor from a nearby process.
So if you only vent and test the inner tank, your worker might asphyxiate before they even reach the hatch?
Exactly. And think about the logistics of rescue. If the worker collapses inside the inner tank, and your non-entry rescue plan involves a mechanical tripod and winch, where are you physically setting up the tripod?
Oh, wow. I didn't even think of that. If you put it on the ground outside the vault, the cable can't reach inside the inner tank.
Right. And if you try to set it up inside the vault, you have the stable floor, it multiplies the complexity of the operation exponentially.
So how do you handle it legally and procedurally?
You must independently evaluate the outer space, establish safety controls, issue a permit for it, and then perform a completely separate evaluation and permit process for the inner space.
Which perfectly illustrates why safety in these environments absolutely cannot be managed by memory or like verbal agreements.
No verbal agreements. Never.
Right. If the physical layout is that deceiving and the gases are actively trying to kill you, relying on a verbal, hey, be careful in there, is practically a death sentence.
It is a death sentence.
That is where the actual architecture of safety comes in. We have to talk about the paperwork, the permit system.
The foundational document is the Written Permit Space Program. OSHA and international safety standards dictate that an employer must proactively evaluate their workplace, identify every PRCS, and write a comprehensive program that outlines exactly how those spaces will be managed.
But the sharp end of the spear, the document that is physically enforced at the entry point, is the entry permit.
Yes, the permit.
Let's really analyze this document. What exactly is the permit doing mechanically? Because to an untrained eye, it just looks like a massive bureaucratic checklist slowing down the job.
It is a situational, highly detailed legal contract for a specific entry. It must detail the specific name and location of the space.
Okay.
It explicitly lists the names of the authorized entrants who are allowed to go inside. It lists the names of the attendants standing watch. It lists the entry supervisor. It defines the exact purpose of the entry and the expected duration.
But the core of the permit is the section that specifies the acceptable entry conditions, right?
Yes. It forces you to document the exact atmospheric readings, and it specifies the physical isolation methods.
Are we locking out valves? Are we purging the space with nitrogen to remove flammable vapors and then flushing it with forced air?
Exactly. The permit demands that every single hazard is identified and matched with a specific implemented control.
And it enforces the stop work authority, doesn't it?
Strictly enforces it. If the pre-entry testing shows combustible gases above 10% LEL, the permit process halts. Work is strictly prohibited.
You don't just put a fan on it and start working.
No. The source of that gas must be physically isolated, the space ventilated, and retested until it falls well below the threshold.
And what happens to the permit after the job is done?
The standard requires that canceled or expired entry permits must be retained by the employer for at least 1 year.
1 year? Why? That seems like a lot of paper to hold on to.
Because the permit isn't just an operational tool, it's an auditing and continuous improvement tool.
Oh, I see.
By reviewing a year's worth of permits, a safety professional can spot trends. They might notice that, hey, Tank 4 always requires 3 hours of ventilation instead of the standard 1 hour.
Which tells them there is a structural anomaly or maybe a hidden chemical residue issue in Tank 4 that needs to be engineered out.
Exactly. In human factors engineering, we know that people get complacent, they do the same job 100 times, and they start skipping steps.
So a permit forces a cognitive pause.
Yes. It forces the supervisor to stop, physically look at the hazard, read the atmospheric monitor, and physically sign their name declaring that the space is safe.
And that signature carries immense legal and moral weight.
Signing that permit is an assumption of profound responsibility.
I want to introduce a scenario here because this is the real-world friction that every safety professional deals with, and honestly, it's something textbooks rarely prepare you for.
I love scenarios. Let's do it.
Let's say you are the safety manager at a large manufacturing plant. It's 2 a.m. A critical valve inside a massive mixing tank fails. The production line grinds to a halt.
We have high stakes.
Right. The plant manager is frantic because this downtime is costing the company $20,000 an hour. The maintenance foreman comes up to you and says, look, I know the tank needs a permit, but it's a 10-minute job. The guy just needs to hold his breath, pop down the ladder, turn the wrench, and climb out.
I've heard this exact speech.
Doing the full isolation, the atmospheric testing, the ventilation, it's going to take 3 hours. We are losing $60,000 just waiting on your paperwork.
How does the safety professional navigate that immense political and operational pressure?
That exact scenario, the clash between production and protection, is the narrative backdrop to almost every multi-fatality industrial disaster.
It's the classic struggle.
The pressure to skip the permit, the illusion that it will only take a minute, is incredibly seductive, especially at 2 a.m. But the safety professional is trained to understand the physical reality. Hazards do not care about production schedules.
Right. Gravity and poison gas don't wear watches.
Exactly. If you bypass the permit and the isolation process, you are flying blind into a potential kill zone. Because what if that valve is failing specifically because it's leaking a highly toxic gas?
Precisely. The worker goes in to turn the wrench, takes a breath, and collapses instantly. Now, the production line isn't just down for 3 hours. It's shut down indefinitely by a federal fatality investigation.
The cost of a fatality far outweighs $60,000 of downtime.
Infinitely outweighs it. The safety professional must have the conviction to explain that the permit is not bureaucratic red tape slowing down the company. It is the armor that protects the worker's life and protects the company from catastrophic liability.
The historical data is unequivocal on this.
It is. We have case study after case study, like the Excel Energy Cabin Creek fire, where the failure to properly evaluate the space, issue permits, and enforce isolation led directly to workers dying.
The paperwork is the physical manifestation of safety discipline. But as we know, a permit is ultimately just a piece of paper. It cannot enforce itself.
No, it can't.
That brings us to the human element. The safety framework relies entirely on a highly trained chain of command at the entrance to the space. Let's explore these distinct specialized roles: the authorized entrance, the entry supervisor, and the attendants.
These roles are strictly defined by OSHA and other regulatory bodies, and their duties absolutely cannot overlap.
Okay, so one person can't be both the entrant and the attendant.
Absolutely not. The authorized entrant is, of course, the person trained and authorized to go inside, recognize hazards, use PPE, and communicate with the outside.
And the supervisor.
The entry supervisor is the overarching authority. They are responsible for verifying that all tests have been conducted, all procedures and equipment are in place, and they are the ones who sign and cancel a permit.
But the role I really want to examine is the attendant. To me, this is the most psychologically demanding and arguably the most critical role on the entire job site. Let's detail exactly what the attendant is doing and, more importantly, where they are located.
The attendant is stationed completely outside the confined space. They never, under any circumstances, cross the plane of the entrance.
Not even to hand down a tool.
Not even to hand down a tool. Their sole, dedicated purpose is to monitor the entrance inside and the conditions outside. They must maintain constant, uninterrupted communication with the workers.
Via voice, visual contact, or those intrinsically safe two-way radios.
Exactly. They're essentially the lifeline. They must maintain an absolute, real-time head count of exactly who is inside.
I think of the attendant like an air traffic controller for the confined space. If an air traffic controller looks away from their radar screen to check a text message, planes can collide.
That's a perfect comparison.
If the attendant looks away, the workers inside are entirely vulnerable. And the regulations are incredibly strict about distractions, aren't they?
They are absolute. The attendant must never perform any other duties that could interfere with their primary monitoring role.
So a supervisor cannot ask the attendant to run to the tool crib to grab a wrench.
No. They cannot help mix chemicals outside the tank. They cannot be scrolling on their phone. Furthermore, they act as the security guard for the space.
Right, keeping out the random folks.
Yes. They have the authority and duty to warn unauthorized personnel, to stay away from the permit space, and to immediately inform the entrance if an unauthorized person does enter.
And their authority regarding the operation itself is pretty much total, right?
Total. The attendant can and must order an immediate evacuation of the space if they detect a prohibited condition.
If the gas monitor alarms, they pull the plug.
Evacuation ordered immediately. If they notice the worker inside showing behavioral signs of toxic exposure, like suddenly slurring their words, acting confused, or losing motor control, they order an evacuation.
What if something happens outside?
Crucial point. If an emergency happens outside the space, say the facility fire alarm goes off or a forklift crashes nearby, the attendant orders the entrance out.
But let's return to that terrifying psychological reality we opened the show with, the heroic fatality. Let's say you are the attendant. Your brother or your best friend is the entrant inside the tank. Suddenly, the continuous gas monitor starts screaming, and you watch your friend collapse face first onto the steel floor.
It's a nightmare scenario.
Every fiber of your human nature screams at you to hold your breath, climb down the ladder, and pull him out. How does a safety program train a human being to fight that instinct, stay strictly outside the hole, and just watch their friend lie there while they call for rescue?
It is the single hardest behavioral modification we have to instill in industrial workers. You cannot overcome human instinct with a casual safety briefing.
Right, a PowerPoint isn't going to cut it.
You have to use visceral, deeply psychological training. You drill into the attendant the physiological reality. If the atmospheric pocket was lethal enough to instantly drop a 200-pound worker mid-stride, it'll drop you the absolute second your head crosses the plane of the hatch.
You have to convince them that going in doesn't make them a hero. It makes them victim number 2.
Exactly. You train them to understand that their absolute best chance of saving their friend's life is to remain outside, immediately summon the specialized rescue team, and attempt to operate the non-entry retrieval winch.
Because if they go in and die, there is no one left to call for help.
And the rescue team now has to extract 2 bodies instead of 1, which takes twice as long.
Which really highlights why the documentation for training is so heavily scrutinized during an audit or an ASP exam scenario. You can't just have a sign-in sheet that says, safety meeting.
No, the standard dictates meticulous certification of training. The documentation must explicitly contain the employee's name, the printed names and signatures of the trainers who verify their competency, and the exact dates of the training.
It's treated like a legal certification.
It must prove that the employee was trained on the specific hazards of the space, the proper use of the PPE, and the rigid emergency procedures. In safety compliance, if it is not documented flawlessly, it did not happen.
So we have built the foundation. We understand the deceptive geometry of the spaces. We know how to scientifically evaluate the invisible gases. We have the permit sign, and we have trained people standing watch.
Now we need the physical tools.
Right. Now we need to deploy the physical engineering controls to actually neutralize the hazards. How do we take physical control of a confined space?
We rely on the hierarchy of controls. A core principle for any safety professional is that you never start by just handing a worker a respirator and hoping for the best.
PPE is the last resort.
Personal protective equipment is your absolute last line of defense. We start with engineering and work practice controls. Our absolute first goal is to sever the space from the rest of the facility.
We sever it.
We must completely isolate the space to guarantee that no hazardous substance or dangerous energy can enter while the human is inside.
And when we talk about isolation, a lot of people immediately think of lockout, tag out, shutting off the breaker to the mixer blades. But in piping systems, isolation is much more physical than just turning a valve off, right?
Immensely more physical. Think about an industrial valve. Over time, the internal seals wear down. A closed valve might still be leaking highly toxic chemicals or high-pressure steam at a slow, invisible rate.
So it's closed, but it's not truly safe.
You cannot stake a human life on a rubber seal. Therefore, strict isolation requires blanking or blinding.
What does that mean physically?
You literally unbolt the pipe flanges, insert a solid steel plate, a blind between the pipes, and bolt it back together. You create a physical, impenetrable steel barrier between the hazard and the space.
Oh, wow. Or you do a double block and bleed, right? Where you close two valves in a line and open a drain valve between them. So if the first valve leaks, the chemical drains onto the floor outside instead of into the tank.
Exactly. You also have to bleed off any stored energy.
Like what?
If there is a massive hydraulic press inside the space, you don't just turn off the power. You have to bleed the hydraulic pressure so the ram cannot succumb to gravity and crush the worker.
You depressurize pneumatic lines, block physically moving parts. You essentially render the space mechanically and chemically inert.
Yes.
Okay, so once we have physically isolated the space from external inputs, we have to deal with the atmosphere inside. And the primary engineering control for that is ventilation.
Correct.
We bring in massive mechanical blowers to force continuous fresh air into the space, diluting and exhausting the contaminated air. But here's a mechanical question that comes up a lot.
Shoot.
If I have a massive fan pumping 2,000 cubic feet of fresh air per minute into a tank, why do I still need continuous gas monitors and harnesses? Hasn't the fan just blown the hazard away?
It is a logical question, but it ignores the physics of airflow. Ventilation isn't magic, and air is incredibly lazy.
Air is lazy.
Air will always take the path of least resistance. If you put the supply duct and the exhaust duct too close together, the fresh air will just travel in a short loop straight out the exhaust, leaving the entire bottom of the tank completely stagnant.
Oh, we call that short-circuiting, right?
Yes, short-circuiting. So the worker at the bottom is still breathing toxic air while the fan blows uselessly above them.
Wow.
Furthermore, tanks have baffles, structural supports, and dead legs where air simply doesn't circulate. And we must remember the dynamic nature of the work, like we talked about earlier.
Right. If a worker is spraying a highly volatile solvent, they might be generating flammable vapors significantly faster than the ventilation system can physically exhaust them.
Exactly. Or, what if the gasoline generator powering the blower suddenly runs out of fuel? The ventilation stops, and the atmosphere degrades in seconds.
That perfectly illustrates the concept of layered defense.
Oh.
You isolate the space, you ventilate the space, you continuously monitor the air, and then you suit the worker up in PPE as the ultimate safety net because you assume the engineering controls might fail.
You always plan for failure.
Let's talk about that safety net. What does PPE and rescue equipment look like in these scenarios?
If the atmospheric hazards cannot be fully engineered out, the worker must wear respiratory protection. Depending on the severity, this could be an airline respirator that supplies continuous breathing air from a pristine source outside the space.
Or a fully self-contained breathing apparatus, right, like a firefighter wears for IDLH environments.
Yes, SCBA. Furthermore, if the space has electrical hazards, we use intrinsically safe, low-voltage, explosion-proof lighting and tools so we don't introduce an ignition source.
But the most critical piece of physical rescue gear is the non-entry retrieval system.
Absolutely.
Okay.
Because we established earlier that we never want to send a human in to do a rescue if we can avoid it.
Right. So how does the non-entry system physically work?
Whenever feasible, we design the entire operation around mechanical extraction. The entrant wears a full-body chest or back-mounted harness. Attached to the D-ring on that harness is a heavy-duty retrieval line that extends all the way outside the space.
I mean, outside, that line is connected to what?
A mechanical lifting device, typically a specialized tripod placed over the manhole, equipped with a mechanical advantage winch.
So if the entrance collapses, the attendant outside doesn't climb down. They simply grab the handle of the winch and crank the victim up and out of the space.
Exactly. And the standard is very strict about when this is required. If emergency escape from the space is difficult, if it requires climbing a ladder or being hoisted, harnesses attached to retrieval lines are absolutely mandatory.
Unless the lifeline itself would create a greater hazard, like tangling in heavy machinery, right?
Yes, that's the only real exception.
And if the space is designed so complexly, like those nested tanks we discussed earlier, the space within a space where a straight line winch simply won't work, what happens then?
Then you are legally required to have a highly specialized, fully trained rescue service on standby.
Like a dedicated technical rescue team.
Yes. And if an attendant is specifically designated as a rescue team member who will enter, which is a massive commitment, they must have their own rescue equipment immediately available, and they must wear at least the same level of PPE as the person inside.
They cannot waste 5 minutes digging through a truck to find a respirator while the entrant is dying.
No. The rescue infrastructure must be ready to deploy in seconds.
It is an incredibly comprehensive, interlocking system of physics, psychology, and engineering. To summarize the massive journey we have taken on this QHSE Talks today,
It's been a journey.
we started by looking at the unforgiving geometry of a confined space, recognizing that human-centric architecture is forgiving, but industrial architecture is a trap waiting to be armed.
Deadly trap.
We explored the invisible killers, breaking down the exact physiological thresholds for oxygen, the explosive limits, and the absolute necessity of continuously testing the atmosphere to combat the salad dressing layering of toxic gases.
The layers of danger.
We navigated the rigorous permit system, understanding that it's not just a bureaucratic hurdle, but a legally binding, life-saving checklist that forces a cognitive pause.
It forces you to think.
We defined the unyielding human roles, specifically the immense psychological burden on the attendant to fight their own heroic instincts and stay out of the hole. And finally, we layered our physical defenses, using blind flanges to isolate energy, strategic ventilation to clear the air, and mechanical retrieval tripods to ensure that everyone who goes into a space comes back out alive.
It requires absolute discipline across every single layer. And as we wrap up this exploration, I want to leave you, the listener, with a final, forward-looking concept to deeply internalize as you prepare for your exam or walk your facility tomorrow.
What's the final thought?
We touched on this, but it must become your baseline philosophy. Remember that a confined space is not a static room. It is a dynamic, highly reactive, living system.
The environment reacts to the worker.
Exactly. A permit-required space might test perfectly clean, with green lights across the board at 8 a.m.
But the instant a worker fires up a welding torch, applies a chemical solvent, or simply kicks up decades of settled combustible dust from the floorboards,
They have fundamentally engineered a new lethal hazard. Your hazard assessment as a safety professional must predict not just what the space is when it's empty, but what the collision between the space and the specific work task will cause it to become.
you are evaluating the collision between the tank and the task. That is a brilliant way to frame it. A dynamic, living system.
That's the mindset of a true safety pro.
I highly encourage you to take this analytical mindset into your ASP studies and, more importantly, into your daily safety rounds. Use this knowledge to spot the invisible hazards that others miss and enforce the controls that bring your teams home safely. Thank you for joining us for this edition of QHSE Talks, and stay safe out there.